In this video, we'll talk about the sign bit and how we can change the size of binary numbers, say from a byte to a word or from a word down to a byte. When writing decimal numbers, we always eliminate leading zeros. We assume that any leading zeros are not significant and therefore they don't need to be written. So these two numbers are equivalent. We can always assume there's an infinite number of zeros going off to the left, but we can ignore those. The same is true of hex and binary. These two numbers are equivalent. So here we've represented one number using 6 hex digits. How many bytes is this? 1, 2, 3 bytes. And here we've represented the same number using 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and possibly more bytes. The leading zeros are not significant. These are both the same number. And again in binary, here we've got a binary value that seems to have about 9 bits in it, and we can add zeros on the left side and it doesn't change the value. They're not significant and they can be ignored. But what about 2's complement numbers? In decimal, well, we don't really use the 2's complement system for decimal numbers. We just put a negative sign in front of it. So the issue doesn't really apply. But in 2's complement representation, we have sign bits at the beginning. So here's a negative number using 2 bytes. Remember, D is something that starts off with a 1 bit. It's 1101. So this number begins with a 1, so it's a negative number. And here we've added additional 1 bits in front. And these are not significant either. Like the leading zeros in positive numbers, the leading ones, or in hex F's, are not significant for negative numbers in signed 2's complement number representation. Here's a negative number expressed in binary. It's got 1, 2, 3, 4. So it's got 16 bits. It's a half word. And it begins with a 1, so it's a negative number. Here we've added 1's to the left. Those are not significant, and it's the same number. So here we've expressed it with 4, 5, 6, 7, 8, 9 times 4, 36 bits. It's the same number. Here's a diagram from the Bryant and O'Halloran textbook showing how we can increase the size of a number, regardless of whether it's positive or negative. All we have to do is take the sign bit and duplicate it. So we call this sign extension. So we're going from a number that has W bits, and here in green is the sign bit, and we're increasing the number of bits by k bits, so we're making it a larger number. And we can do this by copying this bit, whether it's a 0 or 1, into these new bit positions. It doesn't change the value of the number. If it's a positive number, this is a 0 bit, and there are leading zeros which we can always add without changing the value. If it's a negative number, this is a 1, and these are all 1 bits. Again, it doesn't change the value of the number. Here we see some examples of sign extension. We're increasing the size of a binary number by adding zeros, or I should say extending the sign bit. Okay, here's a positive number. First we have it as a byte, 0110 1010. In hex that's 6A. Here's the same number down here, 6A. And it happens to be 106 in decimal. And we're extending it from a byte to a half word by adding 8 more zeros. And we're extending it again to a full word by adding an additional 2 bytes, all zeros. These are all the same value, so we can increase the size of a number by sign extending it. Here's a negative number. We're going to sign extend that. In this case, the number starts with a 1, 1100, 0101. This is C5, same number down here. And this is minus 59 in decimal. And we copy the sign bit first to a half word and then to a full word. And it's the same value regardless. Here we show the exact same values in hex. The leading hex digit indicates that this is a non-negative number. It falls between 0 and 7. And so we sign extend this by adding zeros, first to a half word and then to a word. Here we add 1 byte, and here we add 1, 2, 3 bytes. In this case, the most significant hex digit is a C. Anything that's 8 or greater, 8, 9, A, B, C, D, E, F, indicates that it's a negative number. So to sign extend a number that begins with something like 8 or larger, we add Fs. So here we add a byte of all Fs to get a half word, and here we add 1, 2, 3 bytes of all Fs to get the same number as a word. The next thing we might want to do is reduce the size of a number. But when we do this, we have to be careful that we don't change the sign bit and we don't eliminate significant bits. So here we have a full word, okay? 1, 2, 3, 4 bytes, okay? And it's a positive number because the leading bits are 0. And we are shrinking it down to a byte by eliminating zeros. And these are all zeros, and they are the same as the new sign bit. So we're just eliminating insignificant leading zeros. In decimal, this number is 106, and 106 can be represented as a signed number in 1 byte. So we're okay. We haven't changed the value, and this number is small enough that it can be squeezed into a byte. Here we have a negative number. The leading bit is a 1, indicating it's negative, and we're going to eliminate all the 1s, and the sign bit is still the same, so we haven't changed the sign bit. And this number happens to be minus 59. And so minus 59 is also something that can be represented in 1 byte, in 2's complement notation, so we can safely shrink this thing down from a word to a byte. Here are the same values expressed in hex. 0, 0, 0, 6A can be reduced to just 6A. Both are positive, so you're not changing the sign. And here we have FF, FF, C5, and it stays negative, so the value does not change. Next, we show a couple of examples where we get into trouble. In the first case, we're trying to shrink the representation of 197 down from a word representation to a byte representation. And unfortunately, we can't do this. The problem is that 197 can be represented with 32 bits in sign notation, but it cannot be represented with only 8 bits in 2's complement sign notation. Remember, the largest value with 8 bits is 2 to the 7th minus 1, or 127, and this is larger than that. So we're eliminating what appear to be insignificant bits, but we've changed the sign bit from a 0 to a 1. So what used to be a positive number has now become a negative number, and this is actually the representation for minus 59. So we've got C5, and we've eliminated zeros, but we've changed the sign bit from a 0 to a 1, and so we've gone from a positive to a negative number. Here, in this example, we've eliminated 1s, but again we've changed the sign bit. So the problem is that minus 150 is not representable in only 8 bits. We can only go down as far as minus 128, and we can't go down as far as minus 150. There is no representation for minus 150 with only a byte in the 2's complement notation. So it turns into the number 106. In the rest of this video, I'm going to talk a little bit about the C programming language And if you're not interested in the C programming language, you can skip to the next video if you want. So here are some variable declarations in C. A char is 8 bits, a short is a half word or 16 bits, and an integer is 32 bits. And so given these variable definitions, let's look at these assignment statements and see what happens. We're assigning to C value minus 123, which can be represented in a byte. So when we copy it into a half word, there's no problem. It's sign extended. And when we copy it into an integer, there's no problem. It's sign extended. Here's some print statements. We execute these print statements to print out the value of I, S, and C. And here's our output. We find that the number is still the same. If you want to know what's going on in binary, we can look at it down here. Here's the representation for minus 123 as a byte. See, the leading bit is 1, means it's negative, and we extend it to a half word or to a full word by just doing the sign extension and copying the 1 bit. These same numbers in hex are 85 and FF85 and FF85. Now we're going the opposite direction. We've got the same definitions. C is a byte, S is a half word, I is a word, and we're starting with an integer of 32 bits, and we're shrinking it to 16 bits, and then we're shrinking it to 8 bits, and then we're going to print out the values. And in this case, what we're doing is what C does is it just does truncation, meaning it just chops the bits off. And as long as it doesn't change the value, that's just fine. Okay, in this case, our value is minus 59, which can be represented as a half word or as a byte. So we chop off the bits, and the bits that we chop off are not significant. In this case, because it's negative, we're chopping off all 1 bits, and the sign bit is not changing. So our output shows that all 3 of these variables have the same value. C just truncates. It does it without question, and sometimes this results in surprising answers. And we can say that this is not exactly what we'd like to see happen. So this is a source of potential bugs. So watch what C does in this case. Again, we've got the same variables, 1 byte, a half word, and a word. And we're assigning I to some value, and then we're shrinking it down to a half word and then a character, or a byte, I should say. But in this case, our value, which is 100,000, cannot be represented as a half word or as a byte. So when we try to print out these values, we get different values. So the value is effectively changed by the truncation that C does when we copy a larger bit value to a smaller bit value. We can see what's going on if we look at the actual bits. Here's the representation for 100,000 in decimal. Here we're showing it in hex, and here we're showing it in binary. And let's just look at the binary. We're chopping off bits, and we have different bits. We're not chopping off all zeros or all ones. We're chopping off a mix, so we're losing some significant bits. And we're also changing the sign bit from a positive to a negative. So that's why we get this number. This is the signed 2's complement representation of a 16-bit number for minus 31,072. And then when we chop it down to a byte, we're chopping off a bunch of significant bits. And again, the sign bit is negative in the result, whereas in the original it was positive. So this happens to be the representation for negative 96. So sometimes when we move from a larger size to a smaller size, the value can change if it's not representable in the smaller size. Whatever value we get for the half word or for the byte has to be a value that can be represented in a half word or a byte. And 100,000 is too large to be represented as a half word or as a byte. So we get other values that are not necessarily what we might expect to get. let's delve a little bit more into C. C has the ability to represent numbers in 2's complement notation and also in unsigned notation. So let's look at these examples. The default for variables of any type is signed. So if we want an unsigned number, we have to actually use the unsigned keyword. So here's a short value, which is a half word. And remember that we can say short int if we want, but it's probably better just to say short because int by itself is a word-sized quantity, and a short or a short int is a half word, so it's better to just say short. So I've left off the ints here on all these examples, and that's a typical programming practice for C. And so we're defining a variable x that's of type short, and here we're defining a variable that's of type unsigned short. So by default, x will be signed and ux will be unsigned. And so here we're setting x to a value, and that and then we're casting it here to an unsigned value. We copy the bits without processing, and so we don't change the actual bits in the number. The number of positive numbers that an unsigned can represent is a lot larger than what a signed can represent. So if you've got a positive number, you can always squeeze it into an unsigned number. So here we're casting this thing. You have to say in parentheses unsigned short so that the compiler will not complain. You have to let the compiler know you're doing this intentionally. What you're doing is you're taking a signed and you're moving it into an unsigned variable. So this is called casting, and you have to say that you're doing this intentionally. And as long as x has a positive value, this cannot fail. This will not fail because the range of positive values for the unsigned is larger. So non-negative values will be unchanged. On the other hand, negative values will always be changed. So here we have another example where we have a signed half word, and we're moving it into an unsigned half word. And this time the value of y is a negative number, and you can't represent numbers with the unsigned notation. So it's going to just copy the bits over directly, and what you'll get is a value that you don't expect. Negative values will get changed into large positive values. The sign bit becomes the most significant bit and is no longer a sign bit, but is actually a significant part of the number. In C, we can specify constants in decimal. And if we do so, the assumption is that those numbers are signed. They can be positive or negative. If you want an unsigned constant, and this should say unsigned here, then you need to specifically say that it is unsigned with a U. So the U here indicates that this 0 will be treated as an unsigned value, and that this number here will be treated as an unsigned value. Here's an example showing the definition of some variables. Tx and Ty are signed integers, meaning they're 32 bits each. Here we have unsigned integers. We don't need to say int, so typically we just say unsigned, and that means that ux and uy are two variables that are 32 bits, and they will only carry numbers that are non-negative, 0 or positive. Here we're copying an unsigned number to a signed number, so we're casting it, and this will just copy the bits across. If the most significant bit happens to be a 1 in the unsigned number, that means it's a very large positive number. That 1 in the most significant position will then become a signed bit in the signed version, and this thing will turn into a negative number, so the value will change. If the value of the unsigned number is too large and cannot be represented in the signed representation, then the value will change to something that can be represented. Here we have got a signed number, and we're trying to put it into the unsigned, and we're copying it into the unsigned And again, the bits will be copied over exactly as they are. And if this is a negative number here, that means the most significant bit is 1. Well, that 1 bit will then just be part of the number in the unsigned version, and the negative numbers will get translated into very large positive numbers in the unsigned version. So if the number cannot be represented in the target representation, then the value will be changed to something that can be represented. Signed numbers cannot represent really large positive numbers, so the really large positive numbers from an unsigned will get turned into negative numbers. Unsigned numbers can't represent negatives, so a negative number in the signed will get turned into a very large positive number in the unsigned. It's always best to insert these explicit casts like this so that you know what's going on. Sometimes the compiler will insert these automatically for you and you don't need to. Sometimes in assignment statements and also when arguments are passed to functions. This happens particularly if the functions are defined in separate files. Then the type checking can sometimes be sort of lost. So be very, very careful about the distinction between signed and unsigned numbers, as well as the distinction between numbers that are half word sized or word sized or double word sized. Some compilers will warn about possible issues, and when you see these issues, you should probably always pay attention to these warnings. Usually it indicates you've made an error. It's very rare that you want to do something like this, and you better be sure that the value you're casting will be in range and won't be mutated or altered by the cast. Here are some examples of things that can surprise you. And what we're looking at here are two numbers, okay? And we're asking, what is their relationship? And the ones in black are exactly what you'd expect. If there's a U, it's an unsigned number. If there's not a U, it's a signed number. So 0 unsigned and 0 signed are equal. In C, when there's a mix between signed and unsigned, the signed number is converted to unsigned and the comparison is then done as an unsigned operation. So let's look at -1 and 0. These are both signed numbers, and so the comparison is a signed comparison, and that's just fine. They're both signed numbers, so the comparison works. -1 is less than 0, and that's what C will tell you. Here we've got another example, though, where we get a different result. Here, the 0 is unsigned. So these are the same values, it would seem, except that this causes the C compiler to do an unsigned comparison. So it treats this bit pattern as an unsigned number. Remember, it's all ones, or in hex, all Fs, which is the largest positive number in the unsigned representation. So even though this is a signed number, the bit pattern is the same as the largest unsigned number. That large positive number is greater than 0, so the result is this number will compare to 0 unsigned and be greater than, which is not what you expect. Here we have two signed numbers, and this is just fine. You get the result you expect. It's a signed comparison. Here we're mixing, and we've got an unsigned number and a signed number. Well, it converts the signed number to an unsigned without changing the bits at all. Minus this large negative number is really 80000, and it's a very large unsigned number, and in fact it's slightly larger than this unsigned number, which is 7F, FF, FF, FF. Here we have two signed numbers, so the comparison works. Here we have an unsigned -1, and so both of these are converted to signed numbers, and since they're both negative, the comparison ends up working the way you expect. Here we have a mix, and this signed number is converted to unsigned, and it doesn't change value. So we have two positive numbers, and they compare the way you expect. Here, what we're doing is we're casting an unsigned number to an int, to a signed number. So, unfortunately, this number is so large that it cannot be represented as a signed number. So when you copy over that bit pattern, it becomes a very large, it becomes the smallest negative number. And the result is that the comparison is that this is greater than this. So because of this cast, you get a result that you might not expect. Here is an example in C of what can go wrong if you're not very careful with these signed and unsigned distinctions. First of all, this is telling us that we have a function called string length that's passed a pointer to a string. And if you know C, you know that this function is a built-in function that's in the library, and it counts the number of characters in the string and returns that as an integer of some sort. And in fact, if you look at what size t is, you find it's an unsigned integer. So you have to be careful. This function returns an unsigned number. Okay, now let's say we write a function called string longer. Okay, and it's going to return true or false, which in C is represented as an integer, either 0 for false or 1 for true. And it's going to be passed two pointers to two strings, S and T. And what it's going to do is it's going to look at the length of string S and the length of string T. And if string S is longer, well, we're going to subtract off the length of string T. And if string S is longer, then this is a positive number. And if T is longer, then this is a negative number. And then so we're just going to compare and return either true or false according to this comparison, whether it's positive or not. Well, where we get into trouble, though, is that the string length function returns an unsigned. So this subtraction occurs, but we don't get a negative number. We get an unsigned number, which is always non-negative. So we either get 0 or something positive. So the problem is this thing won't return the right answer. Okay? We'll never get a negative number here. So if string t is longer, we ought to get a negative number here, and we ought to return false. But in fact, we will that negative number cannot be represented as an unsigned, so it will be represented as a large positive number, and this will test true. So if string S is larger, this is a positive number, we return true. If string T is larger, this is a negative number, but as an unsigned, it's a positive number. Again, we return true. So imagine we're using this test to see if something will fit into a particular space in memory. It returns true, regardless of which one is longer. Okay, so we copy the string into the buffer, and perhaps we overrun the buffer space, and this could result in a system security violation. So bugs like this can lead to security violations. Here's another image from the Bryant and O'Halloran textbook. I like this because it shows sort of the relationship of how signed and unsigned work. So on the left we have signed numbers, and on the right we have unsigned numbers. Let's look at unsigned first. The idea is that each one of these red dots is a number, and we start off with 0, and we go up to some maximum number here. So we have a bunch of positive numbers, 0 and a bunch of positive numbers, increasing all the way up to some maximum number. Now let's look over at the unsigned side. We have 0, and we have positive numbers that go up to some maximum, and we have negative numbers that go down to some minimum number. If a number is in the range of 0 to this t max number, then its representation is the same, whether we're thinking about unsigned numbers or signed numbers. we can copy it back and forth. The bit pattern is exactly the same. The value doesn't change. Our problem occurs when we have negative numbers in a signed representation and we copy them to an unsigned. Those copy over into extra large positive numbers, -1 being the largest positive number, and our most negative number being equivalent to a large, but not as large, positive number. And likewise, when we copy unsigned numbers, if they're extra positive, if they're super large, they end up mapping into negative numbers. So this shows the relationship between unsigned numbers and signed numbers. If the value is within a range that can be represented in both signed and unsigned forms, then we can copy it back and forth safely. But if it's a negative number, we can't copy it. Or if it's a number in the unsigned range that's larger than Tmax, then we can't copy it back to the signed value without changing its value. So this is the kind of thing that you have to be especially careful of. Lots of bugs can be introduced in the distinction between signed and unsigned if you're not carefully paying attention to whether a number is signed or unsigned.